Hello and welcome to the course Design Bore Fields with Confidence. This is chapter 4 of the first part, where we will be talking about the building thermal energy demand, which is of course, last time we discussed the ground properties, our next big piece of information we need in order to be able to make a geothermal bore field design. But before we jump into that, I want to say a couple of words about terminology. Because when we're talking about bore field design, we have two types of loads. On the one hand, we have our building demands, expressed in heating, cooling, and domestic hot water. But our bore field does not care about all of that. Our bore field only cares about the energy being extracted from it or injected into it. And of course, there is a link between, for example, heating, where you extract a certain amount of energy from the ground to heat your building, but your kilowatt hours in heating are not the same kilowatt hours as extraction, because there is a heat pump in between. And if you're not careful about terminology when you're talking about ground loads and building loads, you may end up with a wrong design in the end. So in GHG2 you can either work with the building demands or with the ground loads themselves. Now typically you work with the building demands, or you have to estimate some building demand first, which is what we will be doing in this lecture. So when we're talking about the building thermal demand, you can basically have it in two resolutions. One way, which is typically done for feasibility studies, or most projects basically, is you work with a monthly resolution, meaning that you have values for heating, cooling, and domestic hot water in every month of the simulation periods. Now, in GHG2 you can even work with yearly estimates, a yearly energy demand, which is then automatically spread out using a default profile. But that's the way you typically design bore fields. If you have more detailed information available, you can also work with hourly values, where at every hour you know what your heating, cooling, and domestic hot water usage is. And this can give you a way better accuracy of a way better detailed analysis of how your geothermal system behaves. We will come back to that later. So both monthly and hourly resolutions, you can have it with a yearly input, where you assume that, okay, this is my energy demand of my building, and I assume it's the same for every year of the simulation periods. But for example, when you have a phased project and your building is constructed in different parts, or if you have a renovation, and it's done in multiple phases, it can be useful to have a different load for every year. And this multi-year input is also feasible in GHG2 clouds. But for the sake of simplicity, we just stick to the yearly loads in this course, but it can be extended to multi-year rather easily. So if we start talking about the monthly resolution, what do we need? Well, we need peak powers for heating and cooling, as well as energy demands for heating, cooling, and domestic hot water. Now, let us go over them briefly. The peak power for heating is typically the easiest one, because the peak demand of heating from your building is just the peak power of your heat pump. And your heat pump is designed according to certain standards that may vary from country to country or region to region. For example, in Belgium, we need to calculate the static heat loss of the building at -8 or -9 degrees outside. And when we have this power, we size our heat pump. And when we know the heat pump, we know the maximum heating demand of the building. Now, when you have a modulating heat pump, the story is a little bit different. Because, for example, if you have a static heat loss of 7 kilowatts of your building and the maximum theoretical heating demand, and you install a heat pump of 8 kilowatts, this heat pump of 8 kilowatts can actually give or demand 8 kilowatts from the ground, depending on its internal control strategy, etc. So it's important because you can also limit this modulating heat pump to only work with 7 kilowatts. So if you limit it to 7, you can work with 7 kilowatts in the end. If you don't limit it, you have to work with 8 kilowatts, because that's what your heat pump can demand. So oversizing a heat pump is also causing oversized pore fields. So that's something to keep in mind if you're working with modulating heat pumps. Now, in a very early stage, when you don't yet have the static heat loss or your heat pump selected, you can work with some rule of thumbs in watt per square meter based on the emission system or the type of building. There are some tables over in the course textbook over on our website. You can visit them, but always be careful when using these rule of thumbs that they really apply to your climate zone as well. And the last thing is related to simultaneity. When you have, for example, a whole apartment building, not every apartment is going to be heated at the same instant. So this is what we call simultaneity. We will cover that later in this course when we will talk about collective systems. Now, for the peak power and cooling, there are basically two different philosophies. On the one hand, you can say, well, we really want this cooling, it's really design criteria, and then it's basically the same reasoning as for heating. And you have certain standards in order to calculate this cooling demand, or you have also some rule of thumb for that. That is if you design for cooling. Now, perhaps you say, well, it's a residential project. Cooling is a nice to have, it's free, it's passive cooling. We're not going to design specifically for that. Well, then you can just say, okay, we have an emission system, typically for heating. It delivers 15 to 25 watts per square meter. That's our peak cooling we have. So we're not going to design or calculate explicitly our cooling load. We're just going to work with what is already available. And in an early stage, again, there are rule of thumbs based on the emission system, fan coil units, floor heating, wall heating, etc. Available on our website. So that was it for peak power. Of course, we also need the energy demand. And this you can do in different ways. For example, you can work with full load hours, where you say, okay, this is my maximum demand, and I know it will run for 1,500 hours at this maximum demand. Now, if you oversize your heat pump, this will immediately also lead to oversizing your yearly energy demand. So just use the static heat loss when your full load hours is applied to that. It will be more accurate than when you're oversizing on top of oversizing, let's say. There are also rule of thumbs, kilowatt hours per square meter or kilowatt hours per cubic meter you can use. And you have also something which is called the heating degree day method. Now, this is a little bit like the full load hours, but instead of having just one value encompassing everything from climate to building insulation, usage, etc., we're going to make a distinction between building parameters, insulation and so forth, and environmental parameters or climates, let's say, or weather in a specific region. And these heating degrees days are calculated as follows. So we take the weather profile of a certain location, and we're going to set a reference, a baseline temperature there. And here in the graph, it's 14 degrees. And what we say is, okay, when it's below, when the outside temperature is below this 14 degrees, we need to heat our building. And the lower it gets, the more heating we need. And in order to end up with a yearly energy demand, we just calculate the amount of hours multiplied by the difference in temperature. So basically the whole orange area under this curve. Now, what is important is this 14 degrees. It's not the threshold on your thermostat in your building. It's a theoretical value that also takes into account building insulation, occupancy, internal gains, etc. But just to give you an idea how this can be done, typically it's 15.5, I believe, in Europe. Now for cooling, we can do the same reasoning. We also have full load hours, we have rule of thumbs, and we can also work with cooling degree days, which is the same reasoning as before, but now you set a baseline temperature and everything above it should be cooled. And the higher your temperature or the greater your distance with your baseline temperature, the more cooling you actually need. Now, for domestic hot water, the story is a little bit different because here there are building standards. for hotel and residential and apartments, etc., you have different guidelines on how many kilowatt hours per year per person you need to calculate. For example, a megawatt hour per person per year in a residential setting. There are also rule of thumbs of kilowatt hours per square meter of building. Now, I want to stress you one important thing. Namely, imagine you have a house with 3 bedrooms and there is only an elderly couple living there. So we have 2 people, but there can live 6 people. So do you design your geothermal system for 2 or for 6 people? Now, it is my opinion that if you want your geothermal system to be sustainable, you have to make it based on the building itself. But this is of course something you have to discuss with the homeowners and see the impact when you input different values in GHG tool to see how it varies or changes your design. Now that was it for monthly resolution. Now for hourly resolution, this is called the most accurate way, but there is an asterisk because it's not, because you have quite a lot of parameters you can tweak. The insolation, the solar gains, the internal gains, etc., that you end up with a result that's by definition more accurate. It's more flexible. That's a better wording. It's more flexible and it gives you a more nuanced view. And it's also really helpful because if you do an hourly simulation, you see way better how the ground reacts, and you can also make design choices based on that. So you can put solar shading or perhaps put some different glazing in order to make sure that your loads are giving you the best geothermal design it can be. So the interaction between building design software and geothermal design is really interesting. And also when we go to more advanced methods, this hourly resolution will give us way more insight into that. Now, we can find this hourly loads based on measurement data, or we can run it through building simulation software like Vicus District or Vicus Buildings, IDIs, VABI elements, IDSV, and so forth. What also is important is that you have already simulated the building before, that you cannot just take the profile and put it onto another building. And dynamic simulations are really, really sensitive to the building type, the control strategy, and so forth. So please make sure that whenever you extrapolate from certain profiles, that they are accurate and representative. Now, because we will see this later, but hourly profiles can give you quite a lot of insight in your design, but most often they're not available and we're stuck with monthly estimates. So that's why in GHG Tool Cloud, we also developed a method to take your estimates, your energy demands, your peak demands, and to upscale them to an hourly load profile. And this we do with a method based on these heating degree days. So what we do is we say, okay, let's start with a threshold temperature and assume that everything below this threshold temperature needs to be cooled, needs to be heated, and everything above a threshold needs to be cooled. So this is exactly what our heating degree day was. So imagine we start at 14 degrees. When it's colder than 14 degrees, we need heating. What we then do is we take the area under the curve and we scale it with your energy demand. So you estimated your energy. We are going to scale our profile with this energy demand, and hence we have an hourly profile with the same energy demand as what you basically estimated. What we're then going to do is we're going to check if the peak power of this profile we generated is the same as your peak power. Because if it's not, this means that our heating season started too early or too soon. For example, if the peak power we calculated using the scaling with the energy is higher than your peak power, this means that our threshold was put in the wrong place, because our peak power is higher, meaning we had to get more energy on a shorter period of time, leading to higher peak powers. So what we do is we will increase a threshold and say, well, instead of below 40, let's heat below 15 degrees. This will stretchen the periods where we need heating because the threshold is now more critical, it's higher, so we need more times in the year we will need this heating, meaning that our peak power will also be lower. And this we do iteratively until we have an hourly profile that exactly matches your heating demand, cooling demand, as well as your peak power for that. So that's a best engineering approach, let's say, on how you can use the values you're familiar with, the rule of thumbs, etc., and create an hourly profile based on that. You can even say, for example, yeah, our building needs 12 kilowatts, but we only install 10, for example, then it will also automatically do some peak shaving and move away part of the peak load to earlier and later hours so that you stick below your 10 kilowatts. We will do an example on that later in this course. So this was what I wanted to say about the building thermal energy demand. Now, the last piece of information we need is this efficiency of this heat pump to convert our building loads into ground loads. And that's exactly the topic of next video.